Okay, so this question tells us that for any function satisfying f of x is greater than 0, we have the geometric mean f, which is fy equals e to the power of 1 over y multiplied by the integral from 0 to y of natural log of fx dx. And we have to prove that this is equivalent to fy equals a to the power of 1 over y multiplied by the integral from 0 to y of log a f of x dx. So the only difference between the new equation that they want us to prove and the original definition of the geometric mean is that all the a's have been swapped out with e's. So when I looked at this question, the thing that popped into my head was to use a change of base formula. So the change of base formula for the natural log of f of x, well, it is something that you should just memorize and you should know by now if you're prepared to do step. So I'm just going to write it down. So we'll have, I'm just write log e f of x is equal to log a f of x divided by log a e. And so the geometric mean becomes e to the power of 1 over y multiplied by the integral of from 0 to y of log a f of x divided by log a e dx. So we can now take the 1 over log a e out of the integral because it's just a constant that we're multiplying by. So this will give us e 1 over y log a e multiply by the integral from 0 to y of log a f of x dx. And if you now look at the expression that we currently have and the expression that we're looking for, we can see that we have the integral right. We have an integral from 0 to y of log a f of x. So now we just need to show that the thing that e to the power of 1 over y log a e can be changed to e to the power of a to the power of 1 over y. And so we want to keep the 1 over y. However, so if we concentrate on e to the power of 1 over log a e, the best thing to do would be to change the a back into base e so that we can start simplifying via the definition of logarithms and exponentials. So if we use a change of base formula again, we'll get log a e is equal to log e divided by log e a. 1 over log a e is equal to, well, because log e is just 1, it's just equal to log e a. So this exponential here essentially becomes e to the power of log e a, which is clearly just equal to a by the definition of logarithms. And so our final expression will be a to the power of 1 over y times the integral from 0 to y of log a f of x dx as required. Okay, the second part of the question states f of x is greater than 0, g of x is greater than 0, and hx equals f of x times g of x. The geometric means are f, g, and h respectively. Show that hy equals fy multiplied by gy. So the first thing we have to state is that h of x is greater than 0 because h of x is the product of f of x and g of x, both of which are also greater than 0, and so the product must be greater than 0. So now we have to show that h of y equals f(y) times g of y. So let's work out the geometric mean for hy. So it will be hy equals a to the power of 1 over y times the integral from y to 0 of log a hx. And if we now substitute this formula, hx equals f of x multiplied by gx, we will get that this is equal to a power of 1 over y multiplied by y, 0 log a f of x g of x. And by the rules of logarithms, we can split up the f of x and g of x to get that the above expression is equal to a to the power of 1 over y multiplied by the integral of from 0 to y of log a f of x plus log a g of x. And if we now, dx, forgot the dx's, and if we now split up the integral, we will get that this is equal to a power of 1 over y times the integral of y, 0 log a f of x dx plus 1 over y log the integral of from 0 to y of log of a gx dx. And by the rules of exponentials, we can split this exponential up into two exponentials multiplied together, and they will be a to the power of 1 over y integral of from 0 to y log a f of x dx multiplied by a power of 1 over y the integral of 0 to y log a g of x dx. And if we look back to our definition of the geometric mean, that we got, this one here, we can see that both of f of x and g of x are now in this form. So this is equal to f of x, fx multiplied by g of, so this is equal to fy multiplied by gy. And so hy equals fy multiplied by gy. Okay, so the third part of this question asks to prove that for b greater than 0, the geometric mean of b to the power of x is the square root of b to the power of y. So we can use, I think that we can use either of our definitions for this question, but I'm going to use the exponential one just because we're going to have to be integrating, and integrating is much easier with e than with other bases. So our definition will be is e to the power of 1 over y times integral from 0 to y of natural log. And so here we add f of x, and in this case f of x is b to the power of x. So natural log of b to the power of x dx. Now using the rules of logarithms, we can lower the power of b. So this will be equal to e to the power of 1 over y multiplied by the integral from 0 to y of x natural log of b dx. We can then take the natural log of b out of the integral to get that the expression becomes e to the power of natural log of b over y multiplied by the integral from 0 to y of x dx, and now the integral of from 0 to y of x dx will be equal to x squared over 2 from 0 to y, and this will be equal to y squared over 2. So we have that the geometric mean will be equal to e to the power of natural log of b over y multiplied by y squared over 2, which is equal to e to the power of natural log of b y over 2. And as we know from the definition of logarithms, e to the power of natural log of b equals b. So this expression here is the same as b to the power of y over 2, which is equal to b to the power of y and square rooting all of that as required. So the final part of the question is, prove that if f(x) is greater than 0 and the geometric mean of f(x) is the square root of fy, then f(x) equals b to the power of x for some b greater than 0. So clearly the first thing that we're going to do is equate the geometric mean equation to the square root of fy. This will give us e to the power of 1 over y multiplied by the integral from 0 to y of natural log f of x dx is equal to the square root of f of y. So looking at this, we have an exponential on the left hand side, so the best thing in my opinion to do would be to get rid of it by taking the natural log of both sides. We would have the 1 over y integral from 0 to y of natural log of f of x dx is equal to natural log of the square root of fy. And if we take out the square root, as you can do with logarithms, this will become equal to half natural log of fy. If we then, tidy up, we take the y over to the other side, we'll have the integral from 0 to y of natural log of f of x dx is equal to y over 2 natural log of fy. Okay, so once we've ended up with this, we can take the derivative of both sides to get rid of the integral, and so this will give us natural log of fy. This is just a fundamental theorem of calculus, so if this needs more explaining, there are quite a lot of YouTube videos that will explain this, but I'm just going to write it for now. So natural log of f of y is equal to, and then using the product rule, so we'll get, well, the derivative of y over 2 is half, so we'll get half natural log fy plus y over 2 multiplied by the derivative of natural log of f of y, which is just f dash y divided by fy. And so we have that this is equal to half natural log of fy plus y f dash y divided by 2 fy. So if we simplify this expression by taking the half natural log of f of y over to the other side, we will get half natural log of f of y is equal to y f dash y divided by 2 fy. And then if we multiply both sides by 2, we'll get natural log of fy is equal to y f dash y divided by fy. So now this has essentially become a differential equation that we will solve via separation of variables. Okay, so we've ended up with natural log of fy is equal to yf dash y divided by fy. So to solve this equation, we need to differential equation. We need to get all the f of y's except and their derivatives over to one side. So that will give us natural log of fy multiplied by fy divided by f dash y is equal to y. And so at the moment it looks like the left hand side of the equation cannot be integrated as we would want to do. But actually I thought this was quite sneaky. If you invert both fractions, so we get f dash y divided by natural log of fy multiplied by fy is equal to 1 over y. So the right hand side could be integrated. And also if we look at this here, if we divide both sides, top and bottom of the fraction, by f over fy, we will get fy divided by fy over natural log of fy, which if you look closely enough is the natural log of f of y, then above it is its derivative f dash y over fy. So again, this can be integrated, and it's quite hard to spot, but this can be integrated into natural log of fy, and that will be equal to natural log of y, and don't forget the plus c when we integrate. And so if we now raise both sides to the power of e, we will get natural log of fy is equal to e to the power of natural log y plus c, which if we split the fractions will just be, so if I write this out actually, e natural log of y plus c, which is equal to e to the power of natural log of y multiplied by e to the power of c. And if we let e to the power of c equal a, where a is a constant, this is just equal to a y. And so if we again raise both sides to the power of e, we will get that f of y is equal to e to the power of a y. And so if we then let a equal to natural log of b for some b, because of course because a is e to the power of c, a must be positive, and so there must be a value of b such that if we take the natural log of it, we will get a. And so if we let a equal natural log of b, this will be equal to e to the power of y natural log of b, which is then equal to b to the power of y. And so because y in this case is a dummy variable, we can just swap it out for x. It really doesn't matter. And so we'll get f of x is equal to b to the power of x as required.